Good afternoon, everybody. So thank you for inviting me again. It's my third talk at MLConf, as was already mentioned. And I will be talking today about relationship between machine learning and neuroscience. And I will give a few examples of work that we are doing in IBM TJ Watson Research. I'm currently in the group called AI Foundations, but I recently moved from Computational Biology Center, so I'm kind of trying to sit on both chairs, trying to apply machine learning to brain imaging and neuroscience, while also drawing some inspirations from neuroscience to hopefully improve machine learning algorithms. Okay, so I'll give a brief overview of some projects, but there is a long list of collaborators over the past several years who contributed to this work, both from IBM, from several universities and companies. So I would like to thank them all. And as I mentioned, at high level, the kind of objective here is to bridge the two exciting fields of neuroscience and artificial intelligence, where direction from AI to brain essentially means applying algorithms and models developed in AI and machine learning community to better model neuroimaging data and to come up with better explanation of how brain works, again at a high level, while the opposite arrow means trying to draw inspirations and knowledge from neuroscience to hopefully come up with some better heuristics and better algorithms that could improve machine learning. Just to give a few examples of applications where the direction from AI to brain can be useful, I'd like to mention one of the big projects going on in our department currently, focused on so-called computational psychiatry, where at high level the idea is that the field of psychiatry needs to move to 21st century in terms of computational approach to various types of data that can be potentially collected from people, and they are not necessarily collected yet. And examples would include speech, text, video, and so on. All those sources of information can really help you infer changes in mental state of patients and could really automate the field of psychiatry. Another example is health and productivity, closely related to the first one. Don't have to be a psychiatric patient, but for all of us, it would be nice if we could track our mental state and hopefully provide appropriate feedback if the mental state goes into wrong direction, if you're getting too stressed and so on. And in order to do that, you need constantly analyze a stream of data coming from a person using wearable devices or other sensors and machine learning that will help to do it online. Well, yet another example of potential applications of kind of mental state detection online would be safety, prevention of possible accidents on the road, which again often depend on the mental state of the driver, detecting microsleeps using possibly EEG devices or other wearables, detecting lack of attention, detecting stress, and so on and so forth. And finally, the mental state, emotional state detection has tons of other applications in other domains. For example, neuromarketing is a classical one where you try to measure the effect of different inputs, videos, ads, emails, news, and so on the mental state of a person, and you can hopefully decide how to come up with a better ad based on the feedback you're getting from people. Anyway, let's move to a more specific examples, and this is just a high-level overview of several projects that we were involved in the past 5+ years. And in a sense, it's like successful applications of various machine learning techniques in particular disorders with particular data sets and with particular collaborators, starting with fMRI analysis, helping to characterize statistical biomarkers of schizophrenia, and arriving at conclusion that functional networks in schizophrenia are considerably different from functional networks of controls, and features extracted from some networks can be not only statistically very different between the two groups, but can also help you to discriminate patients from controls with very high accuracy, say up to 93%. So this is kind of a promising direction because it's one attempt to help to automate diagnosis, or at least semi-automate diagnosis of mental disorders. Furthermore, another application involved trying sparse models such as sparse regression in video game playing and trying to detect different emotional states and cognitive states of a subject while the subject is playing video game in the scanner. And interestingly, you can, for certain type of states, you can detect them and predict them quite accurately, where prediction is essentially looking at the brain movie of the person and trying to determine whether the person is happy or sad or anxious at this time. Not everything is easily predictable, and it's kind of interesting to investigate which type of mental states are and which are not easily predictable. And another successful application, the third one, was work on pain perception, which was quite surprising because you would think about pain as something very subjective and hard to characterize, and yet with fMRI data, it turns out for quite a few people, you can quite accurately solve regression problem, again using sparse models. Why sparse? Because in neuroimaging, you would like to show interpretable results. And if you manage to predict whether a person is experiencing high or low levels of pain, you also would like to show which brain areas were kind of responsible for producing this. So this is a really nice feat of sparse modeling in neuroimaging applications or any other biological applications where predictability is not the only goal, and interpretability can be just as important because you would like to understand what was going on in the brain which produced this behavior or this experience. There are many more examples, and I'm not going to list all of them here, but I'd like to focus on two most recent projects which involve machine learning in very different ways. And one is more classical, traditional classification, which helps you distinguish how much change a particular medication can kind of produce in patients such as cocaine addicts. So essentially, does it normalize their brain activity and make them more similar to controls or not? So here, classification is primarily used as a tool of measuring change. While the other application is, even more recent one, is really trying to capture spatio-temporal nature of brain imaging using appropriate tools such as recurrent ConvNets, for example. The convolutional nets are pretty good at processing images, making them, while using recurrent ConvNets, hopefully will help you better classify videos coming from the human brain. And after explaining those two examples, at the end, I'll also mention a most recent project on going from brain to AI, where we will use some inspiration from a phenomenon called adult neurogenesis to improve representation learning in sparse dictionaries, for example. Okay, let's take a quick look at the first application where cocaine addiction was studied using fMRI experiments. This is a joint project. It's a collaboration with Rita Goldstein and her group from Mount Sinai here in New York City. So the data were produced at Mount Sinai, and we helped with analysis. But the idea is that, okay, it's well known that cocaine addiction is associated with the fact that cocaine blocks dopamine transporter, and therefore it kind of disrupts reward processing in the brain, and that could potentially lead, although it doesn't necessarily have to addiction. Frequently it does. So the question is, well, can you possibly use a stimulant to counteract a stimulant? For example, methylphenidate hydrochloride, or MPH, commonly known as Ritalin, is a kind of popular drug given for ADHD. Interestingly, it has very similar chemical structure to cocaine, and it acts also in very similar way, essentially blocking dopamine transporters and increasing intracellular dopamine. But its rate of clearance is much slower, which is a good thing to prevent kind of abuse potential and addiction. It doesn't create high. Well, that's why we give it to kids with ADHD, but still there is quite a bit of similarity with cocaine. So the question, again, we are not the first ones, of course, to ask this question. There is a whole bunch of related work, but the question was, can we evaluate effects of methylphenidate on cocaine addiction patients, and can we see any differences? Can it be potentially a therapeutic agent in this disorder? Because similar example exists in other addiction problems. For example, well, nicotine patch, or there is this drug called methadone, which is used for heroin addiction, which has similar action as heroin. So the idea of using stimulant for stimulant is not new, but it's always interesting to investigate to which extent this particular drug can improve brain activity of particular type of patients. We use the data from resting state fMRI, where the patients, well, and controls are placed in in MRI scanner. And in this particular case, it's resting state fMRI, which means that the patients, well, and controls do not really have to perform any task. They just kind of lie down and relax. And the traditional approach in this line of work is to look at so-called functional network connectivity in the images, essentially computing correlation matrix across the whole brain of voxel activations. And then you can look at this correlation matrix and you can threshold it, you can look at the graph, you can basically extract all kind of topological features. And this is old line of classical work where feature construction really matters, because if you suspect something is wrong with networks, you need to look at the network features. So that's what we did in this study, looking at degrees in functional network and trying to see, first of all, how abnormal they would be in patients versus controls, and whether the methylphenidate will normalize them. So basically, in this type of studies, you're not concerned with a particular classifier being the best and the most accurate. You're rather concerned in using the whole ensemble of classifiers. Oops, what happened? Thank you. Yeah, so basically you use classifiers as, what's going on? Okay. Okay, I guess we. So anyway, while we're waiting, I can explain. What I'm trying to say that right now the focus, unlike in classical machine learning studies, is not about which classifier performed best. It's rather, let's use a bunch of them, whatever you can run, whatever is available. Deep networks in this particular study are not applicable because you have relatively small sample size. And that's one of the limitations in certain practical applications in medicine, biology, and neuroscience. You do not necessarily have like millions of subjects there, and you may not have millions of trials. I will talk about another study where deep learning will apply next. But in this one, you essentially use all the classical traditional classifiers, but you use them as a collection just to see whether there is certain trend. And the trend here was that trying to discriminate patients versus controls under the effect of methylphenidate was actually much harder, as shown by increased classification error, which implies that methylphenidate made them more similar to controls, essentially positively answering the question, yes, the stimulant normalized their functional network performance and made it more similar to controls. So yes, indeed, there is a quite noticeable effect, which doesn't mean that you can immediately start using Ritalin and treat cocaine addiction, but it indicates that there is some promise in exploring this direction further. Also, it was interesting that same kind of group classifier approach, just throw everything and see whether there is a trend in behavior of all the classifiers, and yeah. So the results differ, but all of them essentially find it much harder to classify, basically to discriminate. And second example, condition of placebo versus condition of MPH when you have controls. And it's much easier to do when you have patients. What does it tell you? That MPH has a stronger effect on cocaine addicts than it has on controls. So anyway, this is just example that using a classical off-the-shelf standard machine learning in health applications can tell you about medications making or not making difference. The next example is more recent and more sophisticated, because in this example, we really would like to capture spatio-temporal dynamics of brain imaging data. And that's where deep nets, particularly recurrent ConvNets, seem to be quite useful. In this application, we were concerned in figuring out just how much of a memory load a person experiences. It's kind of a classical experiment where you show a person several symbols from 2 to 8, and then after a while there is a kind of short rest period, then a symbol appears on the screen and the person is supposed to tell you whether that symbol was seen before or not. Well, it's easy to see that if you only saw 2, it's easy to remember. If you saw 8, it's harder. So overall, you have these 4 different levels of working memory load, and you would like to know how hard the task was just by looking at EEG data of each particular subject. It could be applicable to various settings in education and in health in general. You can try to measure the memory load of controls versus patients, and so on and so forth. But the question is, can you really arrive at good classification accuracy across those memory load, and what type of techniques would be best? So as classification problem, you just say, okay, for each person, I have multiple trials of seeing different number of symbols and trying to answer whether you've seen a particular symbol or not. So you have, from deep learning perspective, maybe not too many samples, but still some decent amount, roughly 2,600. We only used samples where people answered the question correctly. So you do typical classical EEG data preprocessing, and you extract them. Basically, you do FFT, you extract different frequency bands, and we used only 3 of them, theta, alpha, and beta, because in memory load, in the literature, it's known that those 3 are most relevant to this task. And then you essentially try to evaluate various classifiers, including the ones built on top of recurrent ConvNets. So the idea here was to actually, the novelty was to actually create a movie, a brain movie from EEG signals. That's what people usually do not do in EEG analysis. They just treat them as time series without spatial information. But if you actually project the electrode locations onto 2D and use like standard approach like this azimuthal equidistant projection, you get an image. For each frequency, each of the 3 frequencies, you get a separate image. And you can think now about each frequency corresponding to a particular color. So you have RGB. That would be like 3 layers input to a ConvNet. And then you make a movie by combining different frames that you measured during single trial. So essentially, you're going to have like 7 frames of colored images. And now you can ask yourself a question: what are state-of-art architectures for movie classification, and whether those architectures and their modifications can be useful in brain movies? Because it's still not guaranteed that recurrent ConvNets going to work here. They might work well on natural videos, but the brain videos are not the same as real-life videos. In real-life videos, frequently you have static background like a room and maybe a few people moving through the room. In brain, everything constantly changes, so it's very different type of videos. So it's an interesting question to see whether recurrent ConvNets can do well here. So first we tried static ConvNets. You basically play with different architectures. You kind of increase the number of ConvNet layers. And, well, not that surprisingly, increasing them up to 4 produced best results. And that was like the architecture in the last column when you have basically 7 layers of convolution intermixed with max pool. Yeah, it was about 1% better than shallower architectures. But even better results were achieved when you actually included time in the model. And there are different ways of doing this. One was just simply basically doing temporal max pool. That was architecture in the left top corner. Another was simple temporal convolution. Then we also tried, of course, LSTM structure. The best combination was actually having LSTM and temporal convolution, and the reason, like how we found out, it turned out that for some subjects, LSTM architecture worked best. For other subjects, just temporal convolution worked best. So if you combine both, obviously you cover the whole spectrum. So yes, the result was indeed considerably better than what the state of art was previously on this type of experiment using standard classifiers. So you improved almost up to like 9% your discriminative accuracy across these 4 classes of memory load. And the best result was achieved, as I mentioned, when you combined, first of all, spatial information of EEG with temporal, and you combine both LSTM and temporal convolution. But the important question here, which always arises in biology applications and neuroscience in particular, you're looking at brain, and even if you classified something, the question remains, what type of patterns, what type of representations did you learn that made this classification so accurate? And therefore, mapping back from the features learned to the brain maps was quite important. And we had to use deconvolution here, essentially looking at features extracted at different layers of ConvNet, mapping them back using this basically Zeller and co-authored method of deconvolution, just to see what kind of brain activations correspond to those maps, to those features. And it was reassuring to see that we did see activity that was previously indicated in neuroscience literature on memory loads kind of studies. So examples like frontal theta, frontal beta activity, they're kind of well-known markers associated with memory load tasks, and there were several others. So important point here is that if you apply any kind of machine learning method in neuroimaging or similar kind of biological domain, you may need to keep in mind how you're going to interpret your results, besides just constructing a complicated representation that classifies well. By the way, the code for this is publicly available on GitHub, thanks to a student who worked with me on that the previous summer, Poya Bashivan. So the code is there. It's in Python, based on Theana, and yeah, you're welcome to download and try it on whatever movies, including EEG or something else. Finally, I would like to reverse the arrow going from AI to brain and see what we can get if we go from brain to AI. What I mean here is another kind of activities, as I mentioned. So what if we try to look at some phenomena we know about in the brain and try to understand and model it computationally, hoping that maybe we can get some intuitions to improve existing machine learning algorithms. Again, it doesn't necessarily have to be brain-inspired. You can improve them in many other ways, but it's just interesting if you can draw some inspirations from how brain works. And after all, pretty much the whole of machine learning can be viewed as, well, brain-inspired field. In this particular project, which is actually going to be presented at iClear in France in a month, we decided to look at an interesting phenomenon called adult neurogenesis. Like surprisingly, well, not surprisingly anymore, but it was surprising like a few decades ago, it was found out that adult brains still produce new neurons. So you still grow new neurons no matter what age you are, but in very specific regions. Particularly in humans, it's hippocampus, while in other mammals, like rats, it's hippocampus and olfactory bulb. I guess in humans, olfaction is a bit less important than in rats. In any case, hippocampus is known to be responsible for forming memories, and apparently neurogenesis occurs when a subject is exposed to richer and frequently changing environment. It kind of suggests that if you need to form new memories, if your environment changes frequently, you need more representation capacity. So it's not enough just to adapt the weights, synaptic weights in your network. You need to increase complexity and capacity of your network by adding new nodes. One simple approach, of course, you can try and model it immediately in a deep network, or you can try to understand computational advantages of neurogenesis model in a simpler kind of first step type of representation learning. How about just sparse coding, dictionary learning? So dictionary learning is like a classical approach where you assume that your data can be decomposed into product of two matrices, like in this picture. And one matrix contains dictionary elements, like colored rows in the second matrix, while the first matrix is a sparse weight vectors or encodings, sparse encodings, that help you to combine dictionary elements to approximate your data. Dictionary learning has immediate network kind of visualization and counterpart as sparse linear autoencoder. And essentially, you have to learn, given the inputs, what your encodings or activations of hidden units going to be, and what your weights on the outgoing links or links in that second layer, what they're going to be. So the links on the second layer correspond to dictionary elements, and the encodings correspond to the hidden unit activations. So the trick here was, okay, so this is classical known technique. It's one of the simplest way to learn representations, just single layer. But what if the environment changes and you have non-stationary data, and the complexity of data can increase and decrease as you go, so you would like to keep adapting your model? Well, you can start adding, say, random elements at every iteration when you see a new batch of data, but then your model, your neurogenetic dictionary will grow infinitely, potentially. So you need to counteract the birth process with the death process, and it also has biological connections because in neurogenesis, both birth and death are present. Not every new neuron survives, and the old ones die as well. And apparently those which are not useful for representing information anymore. In terms of sparse dictionary, you can implement births, as I said, by just adding random projections, and you implement this by using group sparsity, L1, L2 sparsity, that will decide whether to keep or to kill dictionary element or the corresponding neuron, depending on how well it performs in terms of explaining the data. Basically, you form objective function and you add those regularizers that will kill the unit if needed. So that's roughly the idea. The details are in the paper, which is on our archive. The nice thing about this approach, the promising thing is when you test it in a non-stationary environment, for example, you change the images that you feed into your algorithm from CT images like this Oxford images on the left, suddenly you switch from city environment to natural environment and you show flowers and animals. It looks like using fixed size dictionary, the baseline, learns not as well as the adaptive approach does. The adaptive approach in those figures, at the same size of the dictionary, approximates input much more accurately. So indeed, it seemed to work, and it works even better if the change in the environment is more drastic. I'm not going to go into all the details, and actually I would like to know how I'm doing in terms of time. Bottom line is that neurogenesis doesn't seem to hurt if the environment is static, but it definitely seems to be advantageous when the environment is non-stationary and the input data start changing. So that's kind of promising direction, and we would like to continue kind of developing more brain-inspired adaptive architectures. And of course, it's a new exciting field. There are multiple papers in this area using different approaches with a common goal of adapting the model in online setting to changing data and changing tasks, changing complexity of the input. So I'd just like to conclude with a few messages learned from the studies on neuroimaging data. First of all, as I mentioned, in brain imaging applications and many actually other biological applications, the data sets are relatively small in a sense of maybe thousands of samples, but not millions or hundreds of millions, unlike some other applications of deep learning. And the second important part is, besides accurate classification or regression, you are very much concerned about interpretability of your results, and your major focus is finding patterns that are predictive besides just predicting well. And in terms of deep learning, that kind of creates particular challenges because usually the focus of deep learning models is not on interpretability, and you need to do additional steps such as deconvolution and so on to make sure that you can interpret the representations you learn. The features can be mapped back, for example, to the brain image. And then you can try to understand whether it makes sense from, say, neuroscience perspective. And another challenge, relatively small data, calls for deep learning with more stricter regularization, trying to make really large-scale models work on moderate-sized data sets. And that's another exciting direction that many people are kind of looking into, just from big data to moderate-sized data. And finally, as I mentioned, the brain-inspired algorithms is an attempt to draw even more inspirations from phenomena in the brain that we know about or exploring, and try to improve machine learning algorithms with those intuitions. Thank you.